my family. Why
is it crooked?
Sprinkled in between my arteries and veins are violets and violets, if you say it's sin. My socks are warm for the red, the soil for blue, my dance my feet. White silk sunlight for my smiles, and this yellow my heart does beat. And purple, the one you so despise, is nurtured by hands that fight and kisses under blue skies. I refuse to let you tell me that these delicate skills I give so freely are what is doing the harm. I like that. Thank you.
All right.
Thanks. I was like all fired up. I was like, I gotta write a poem about these.
Quiet down, everyone. Let's get started. Caleb. Okay, so these are called Riemann sums. You're going to see pretty soon they're connected to integrals. So, all right, let's just get into it here. I'm giving you a function here, y equals 2 to the x minus 1. That's one that shortly down the road we will be able to integrate by hand, but not quite yet. So this is a general idea of like, if you feed a really wacky function into a computer, and then say, or it doesn't have to be a computer necessarily, it could be done by hand, but you can say, what's the integral of that function between, say, 0 and 4? What might the computer do? Well, the computer might say, well, I know that an integral is like an area, so what if I just brute force the area? What if I just break the area up into a bunch of little tiny rectangles? And I'm a computer after all, so I can calculate those areas really fast. And that's the idea. So let's do the left-hand Riemann sum for this function. So the function is y equals. We might as well make a table of values for this because we're going to use it a couple times. So here's x, here's y. Now you have your chart, your little graphy paper here. It's going to hopefully make it pretty straightforward. But when x is 0, we get 1/2. When x is 1, we get 1. When x is 2, we get 2. When x is 3, we get 4. And when x is 4, we get 8. And that's all we can see on our graph here. Any questions so far? Feel okay about that? Okay. So here's 1. What is that? Let's see.
No, it's fine.
Okay.
We're all fine here now. Thank you.
Fine.
How are you? Oh my god. Negative. Oh, it's such a good scene. Okay, sorry. Dale, I told you I got 2.5 hours of sleep last night, so if I get to be too much, just send me out.
There are 4 subdivisions. That's what it says. It says use 4, because a computer might want to do 100 subdivisions. You might want to split this up into 100 rectangles, because that's more precise. But 4 subdivisions. Now the left-hand Riemann sum would be, each subdivision is, so the first one's between 0 and 1. Left-hand subdivision means use the left-hand side of that little interval to make your rectangle. So it would look like this. The first rectangle would be like that. What's the height of that rectangle? 1/2. Do you see why it's called the left hand?
Yeah.
So this interval between 0 and 1, there's a left hand to that interval, 0, and there's a right hand to that interval, 1. So when we do the right hand Riemann sum, we'll be using the 1. But for now, so let's see, what's the area contributed by that rectangle? How much area does it contribute? Well, the height is 1/2, and the width is 1. So maybe you can see the pattern already. What's going to happen? It's going to be y values multiplied by widths.
But would the width always be 1?
In this particular case, the widths are all 1, but what the width could be 2. The width could be 5/7. It could be anything, right? You can see if you did 1 billion, or say 1,000, if you did 1,000 rectangles, the width would be 4 thousandths, right? It'd be really small.
Yeah.
So anyway, let's look at the next interval between 1 and 2. What's the left-hand side of that interval? 1. So we're going to use 1 to generate the height of our rectangle. So on your paper, that should have been, you should have got a 1 by 1 square there. So 1 times 1. Next interval is between 2 and 3. What's the left-hand side of that interval? It's a 2, so we use 2 to generate our y value. This guy, you should see a height of 2, so it would be 2 times 1. And then the last one, the left-hand side of this interval is 3, so we use the y value associated with 3, which is 4. So, what's our Riemann sum in this case? The Riemann sum would be, let's see, 4, 6, 7.5. Feelies?
Yeah.
Okay, let's do the right-hand Riemann sum. That was left. Yeah, the liberal Riemann sum, exactly. Okay. Right-hand Riemann sum. So same intervals, 0 to 1, 1 to 2, 2 to 3, 3 to 4. So the first interval, which one do I use? The 0 or the 1? Well, the 1. I use the 1. So start thinky-winkying about what kind of estimates? What kind of estimate was this compared to the true area under the curve? This is an underestimate, right? This one's going to be an overestimate, and you can start to think about what kind of will the right Riemann sum always be an overestimate? Depends on the shape of the function. And so let's see, the first rectangle was 1 by 1. The second rectangle is 2 by 1. The third rectangle is 4 by 1. And the fourth rectangle is way up here, 8 by 1. Are feelings good about that?
Yes, very good. Good
Very
feelings. We're all fine here.
15 we got for the right hand. What, Jesse? What are you talking about?
My favorite Star Wars scene.
Which scene is that?
The one I showed you where Han Solo, they're breaking into the Death Star and he gets on the little comm link.
Everything's okay here.
We're all fine here
How
now,
are you?
thank you. How are you? Yeah. Negative, situation normal. So good.
Yes.
Like the
Very
4 and the 4 and 8 X values on the updated one.
I'm sorry, it just.
What was that?
The 4 and the 8 X and Y, on the graph.
So this point is 4, 8. Yep.
Why didn't we add that into the?
Because we did 4 subdivisions, and on each interval, each horizontal interval, we used the left side of that interval to get our y value. So, notice this one. Which y value did we not use on this one? Did I say y or x?
You said which one?
Which x value didn't get? Because if you think about it, 4 subdivisions uses 5 x values.
Yeah.
0, 1, 2, 3, 4. On the right-hand Riemann sum, you don't use the 0. On the left-hand Riemann sum, you don't use the 4.
Yeah.
Okay. Midpoint Riemann sum. I'm going to try my best to draw this one. Here's 0, 1, 2, 3, 4. So, doesn't take a huge stretch of the imagination. What x value do you think we're going to use on the first interval? 1/2 halfway. So you're going to use the midpoint of each interval. So this guy I'm trying my best to show this. This y value, well, the width is 1, so 1 times, but that's a good $1 million question. What is that number? What's the y value there?
3/4 or 2/3 something.
7 halves.
I don't think so.
7/3.
There's a
Is it root 2?
that's
1 over
much closer, because if you plug in 1/2 into this, you get 2 to the negative 1/2, right? Which is 1 over root 2.
Oh,
You okay with that?
That's 2 cookies.
Okay, 2 because you knew that one.
I knew that.
So let's just write it as 2 to the negative 1/2. And then this guy, the next one, what number, I messed up my picture, dang it. So notice what I'm trying to do here is take the middle value and then go up and say, that's my y value. Do you guys see what I'm doing there?
You just,
Yeah.
it's the middle value of the curve within that area.
No, it's the middle x value
Uh,
plugged into the function. Does that make sense?
Yes.
So like this one, I just say, what's halfway between 0 and 1? Well, 1/2, plug 1/2 into the function, and that's the y value. That's the height of the rectangle. And then here, the middle is 1.5. If I plug 1.5 in there, I get 2 to the 1/2 power. Root 2 times 1, the width is 1. Let's do the next midpoint. Next midpoint is 2.5. If I plug 2.5 in there,
2 to 3.
I get 2 to the 3/2 power. And lastly, last interval, again, 3.5, just ballpark it. It's a good estimate. As far as drawing out the graph. So this y value would be 2 to the 5/2 power.
Fancy schmancy.
You feel okay about that?
Mm-hmm.
Okay. Yes, Aiden.
I'm confused on how you got you just plugged your x value back into the original equation, right?
So if I wanted a relevant table that I used for this, I would say, well, the x values that I really cared about were 0.5, 1.5, 2.5, 3.5. And the corresponding y values were these 4 numbers, respectively. Is that a yeah?
Yeah.
BT dubs. This is looking like a better estimate, right? Because it did overcount. See how it went over the curve a few times? Well, 4 times. But it also had some gaps. So those gaps are going to, in some sense, cancel-y-wancely a little bit. It's not perfect. Here, I'll, because you guys are such valued students,
Calculator in this class?
I'll do, no, wow, evil, right?
I'm leaving.
So this is that, add square root of 2, then add, this is actually, isn't that just 2 root 2? You actually probably add this up by hand, right? Because this is a root 2, this is 2 root 2, and this is 4 root 2. Anyway.
Well, Mr. Hall, if you really, can you just take the left hand one and the right hand one and add those values together and then divide by 2?
That would get you
That's
a,
what I was thinking.
well,
I mean, it would be really close.
that would get you a good estimate. That would certainly improve the estimate, but it's not going to be perfect. So if you add this up, you get roughly 10.6. Let me emphasize that. Roughly. Which is kind of close to the average of those.
22.
But since this function is nonlinear, there's no reason to expect that averaging those two is going to generate.
Because averaging those two gets you 11. So.
Oh, yeah, never mind. Yeah, it's not even that close to the average, is it?
It's pretty cool.
It's okay. Close enough for government work, as Michael J. would say. Yes. So,
Close enough for $5 gallon gas price.
yeah. Maybe I can afford an Apple later. Probably not.
As long as you just do a good job with your side hustles.
There you go. If I side hustle on my way to the grocery store, I can afford 1 banana. Okay, anyway, trapezoid time. Trapezoid. Is that was the midpoint, in case it wasn't clear. Trapezoid. Okay. Here, I'll just erase all of it. Are we doing good today?
Solid thumbs down, man.
Solid thumbs down.
Again,
That's
two
not
and
lit.
a half hours. Not enough.
Just close your eyes.
Yeah, see more.
It's sunny.
Okay, I'll close my eyes right now for the rest of the period. Work
Don't you know
on.
that insomniacs just need to try harder? They just need to close their eyes really hard. Isn't that the cure, guys?
Yeah.
If you feel tired, just wake up.
Wait, what? If you feel tired, just wake up.
Yeah.
Oh, like become more awake.
If you can't afford the cost of living, just have more money. Right, Callie Jo? Callie Jo.
Do you have a snack that I can have?
Yeah, what do you
I
want?
hardly drink.
I don't know.
What
What snacks do you have?
My brain has so much damn.
Vegan snacks.
Okay.
There's Honey Nut Cheerios.
Sure.
There you go.
Very helpful.
All right. Let's do a little bit of a review first, guys. So,
Trapezoid the house.
trapping out the bando. Here's a trapezoid. Now I drew it in a way that might be a little weird, but I hope you understand why I chose to draw it that way. A trapezoid will typically have two bases. We call it two bases, but the bases are these are parallel. Okay. So I'm going to call this one Y1 and this one Y2. Why didn't you call them B1 and B2? Well, look at what we're doing. Where do you think the trapezoids are going to live? I mean,
On the graph.
it's going to live on the graph. This is the orientation we're going to be dealing with when you draw trapezoids in here. So, what are these y values? Well, I should say, what are these bases? They're going to be the y values from the function. So what's the area of this trapezoid? Well, there's a whole idea of, I make a rectangle out of it and then cut it in half. So you know what I'm talking about? Here's the derivation. You'd say, what if you made a copy of this trapezoid? Now it's a rectangle, and this is y2 and this is y1. So therefore, the area is the area of this rectangle. Let's call it the width. It would be y1 plus y2 multiplied by the width. That's the rectangle. But wait, I only want the trapezoid, so I got to cut that in half. Yeah, bruh?
Oh,
Is that a yeah?
yeah, that makes a lot of sense.
Look familiar? Maybe?
I was never told that's what that formula came from.
Excellent. Well, there you go. Okay, so it's like how the area of a triangle, you get that from going, what if you copied the triangle over and then you had a parallelogram?
Yeah.
Anyway, so there's the formula for the area of this trapezoid. So on this one, watch what happens. Let's just go ahead and derive the trapezoid formula right here. We're going to be kind of sneaky, so protect your neck.
Wu-Tang reference.
Yes. Aaron put one of those on his calculus quiz.
Accidentally. Did you bring the ruckus or something?
He wrote diversify your bonds. He said this integral has irrational bonds. I was like, nice, Aaron. Thanks, bro. That lifted my spirits. Okay.
I didn't know you were with me.
Well, I turned it in, and Mr. Hall looks up at me and smiles. I was like, did I just fail that by not looking at it? I did so bad on it. But then, try that again.
All right. Do you see me constructing? I'm trying my very best to construct these trapezoids. Do you see them?
Beautiful. Looks like the Golden Gate Bridge.
Now you can see trapezoids do a much better job than rectangles, don't they? Because they have these slanty tops, right? And the slanty tops can more bigly hug the curve. Now,
Abrazo.
thinking about the curve, the concavity of it, will this trapezoid be an overestimate or an underestimate?
Under.
over. Because the curve is like
Under
this.
the,
So when you draw a trapezoid on it, that's an exaggeration, but you get a little bit of extra space above the curve.
Mhm.
If it was concave down, the opposite would be true. It would be an underestimate.
Yeah.
Yeah? You feel good? Okay, now what I'm going to do real quick is say, 'cause I want you to see the formula. There's a famous formula here. I'm going to call these y values. This y value, I'm going to call it y0 because the y value at 0. I'm going to call this y value y1, then y2, then y3, and then y4. Do you see? Do you feel me? Maybe, possibly.
yeah,
Okay.
Felix and
Now the
Dave.
reason is we're going to sit because you probably were thinking, if you were thinking, I wouldn't recommend it, but like, bruh, that's going to be a long expression to have a bunch of this. So anyway, it simplifies. Watch. So the first trapezoid, and I'm going to use W too. So I'm just going to take this opportunity to generalize so we have the formula. So let's say this was W. We know it's 1, but say it was W. You go, oh, okay, well, this first trapezoid is 1/2 times W times y0 plus y1, right? That's the first trapezoid.
Yeah.
Plus 1/2 times W times, look at this next one. It's y1 plus y2, right? For the next one? Yep. How about the next one? It's 1/2 times W times y2 plus y3. And the last one is 1/2 times W times y3 plus y4. Do we understand?
Thinky winky, yes.
Is there
Think
like a
it-
faster way to do that?
Nope.
Oh, I thought you were gonna.
No,
do
he's
that.
gonna show.
No, when I said that we're going to derive a smaller, simpler formula, I was lying. That was all just a trick, just to upset you.
It is bananas. They're all bananas.
It's a trap!
Okay,
Oh, you were joking.
Oh my God.
factor out
Boy.
all 4 of these terms have a 1/2 W. 1/2 W, it's factored out then. You're like, wait a second, that's incredible. Now, when I factor that out, look what's left over. I'd have y0 plus y1 plus y1 plus y2 plus y2 plus y3 plus y3 plus y4. So how many y0s did I have?
One.
Just one. But everything else,
Two.
Two.
I was
Two.
saying to you.
2. So there's 2 y1s, there's 2 y2s, and there's 2 y3s, and then there's only a single y4. So think about the moral of the story. This is a nice general formula for the trapezoid. This is the trapezoid formula, as it were. So what you have is the end, the bookends, so to speak, of the Riemann sum just have one contribution each, but all the internal ones have 2 contributions each.
Yeah.
Yeah?
Yeah.
Yeah? So, okay, so applying it to this function, you'd go, what's the width?
1.
1. To quote Ghostface Killah. Y0 was, yeah, good meaning, right?
Yep.
Was 1/2. And then y1 was 1, so 2 times 1. And then y2 was 2, and y3 was 4, and y4 was 8. So this is going to come out nicely, I think. Wait, does everyone understand that?
Yeah.
Yeah.
So again, those 1, 2, 3 internal segments contributed twice apiece. 8, 12, 14 and a half. Half of 14 and a half is 7 1/4, right?
Yeah.
Is that right? Wait, did I get that right?
Less accurate than the one.
No, I didn't say that right. Sorry. 16, 20, 22. Oh, it's 21. It's almost mean number. Gosh. Life is pain.
Life is pain. 11.
Dang it. 22 and a half, so it's 11 1/4. Did I do it right that time?
Who knows?
Sure.
Really, that's taking isn't that the sum of the left hand and right hand divided by 2?
I think it is, or at least it's close to it.
I think that is 11.
Well, 7.
Here, I'll do it. I'll do it.
Because the 7.5 is 15, so it'd be 11.
Yeah,
Yeah,
I think
it's
you
11
can,
and a
yeah,
quarter.
the trapezoidal would be the average of the right and left, I believe, yeah.
Winky, winky, big brain.
Because if you think about how the left hand is y0 plus y1 plus y2 plus y3, and the right side is y1 plus y2 plus y3 plus y4, you add them up, those each appear twice, those each appear once, then you divide by 2 for the average. Yeah, that makes sense. Okay, last thing, guys. Let's compare, so taking bets, what's the actual area? So let's suppose, so this is all getting at this idea of 11. These are approximations of this quantity, right?
Yeah.
I can ask Mr. Computer here. I can say, Mr. Computer, what is the integral of 0 to 4 of 2 to the x minus 1 power? I'm just typing into the computer here. Computer tells me that it's roughly 10.82. Okay, so you can see the trapezoidal Riemann sum was a significant overestimate. It was off by, what, roughly, not quite 10%. Maybe 5%, really, right? It's actually a pretty good estimate of this. So,
Yeah,
you guys feel okay about that?
yeah.
All right. So tomorrow, let's have a work day. I will be here. Very sad.
Oh, sad. I mean, lit about the workday, sad
Are
about
you taking a mental health day?
No.